Thank you very much for the invitation. And so to be more precise, actually 10 years ago, exactly 10 years ago, most of the results what I'm speaking now seem to be completely inaccessible to the existing methods of number theory. The situation changed already 9 years and 10 months ago by the result of Green and Tao, but actually what we will see here is still in that respect all contributions are from the last 10 years to be more precise. So I will begin just with some notation. Was it just, yeah. Yeah, so the P will denote the prime numbers, Pn will denote the n's prime. If I put a asterisk perhaps or some other sign, then the index doesn't mean that it's the i's prime. And then I put dn for the n's difference between consecutive primes. And we will call an even number 2k a Polignac number if dn equals 2k infinitely often. So you see this is a far-reaching generalization of the twin prime conjecture, and it was first formulated in 1849 by de Polignac. And the definition comes from this source. Now you should not wonder that you did not meet the definition of Polignac number too often, since until very recently, some year ago, no Polignac number was known at all, so that means there was not so much need to have a definition for it. But so that means we could say a Polignac number is a number which satisfies the twin prime conjecture. I have to say that we don't know any concrete Polignac number still. This seems to be the same difficulty as the twin prime conjecture, but nevertheless we know already a lot about Polignac numbers, as you will see later from the lecture. We will still use the notion smooth or friable. That means a number is y smooth if all its prime factors are below y. And we call n as an E2 number or semi-prime if it has exactly 2 prime divisors. This has to be distinguished from the older and more common notation P2, which means that the number has at most 2 different prime divisors. Different or equal, it doesn't matter. It has at most 2 prime divisors. Now, if we go further a little bit, Möbius, mu1 is the Möbius function, and we will use the abbreviation I.O. Which means infinitely often. If for a formula you see this I.O. at the end, that means usually the formula is true for infinitely many values of n. The running variable will be usually n, and I.O. means infinitely often. Now, if we go to the first section, small gaps between consecutive primes, then I will now, you know probably that there are 2 directions now already to prove bounded gaps between primes and consecutive primes. And I will first begin with the first approach, which was so to say announced, and even the manuscript was made public by Zhang in May 2013. So I repeat now the twin prime conjecture, the Polignac's conjecture. We call the small gaps conjecture that we have arbitrarily small gaps between consecutive primes compared with the average gap size, which is log n. So that means this delta means that the relative size, the normalized size of twin primes, not twin primes, of consecutive primes is just can be as small as we want. This is naturally still far from the bounded gap conjecture. What we introduced that there is a constant such that the consecutive prime differences are less than this constant infinitely often. It turned out this conjecture was not introduced before because there was no mean to access this conjecture, but as in our work about the small gaps conjecture with Goldston and Yildirim, we almost could show the bounded gap conjecture, so we introduced the notion of bounded gaps conjecture. When I say we could almost prove, you have to be careful because, for example, in the lottery, at least if we consider the Hungarian lottery where you have to choose 5 numbers among 90, then the probability that you can choose all 5 numbers with distance at most 1 from the really chosen number is, roughly speaking, 243 times more than to have really the jackpot. So that means if you have just almost a jackpot, this means you might gain just a few euros or even nothing. So one has to be careful with this notion when I say we almost proved the bounded gap conjecture, but it will get a precise meaning later on when I spoke about the ideas of the proof. Now, concerning the bounded gap conjecture, the bounded gap conjecture means that if we have below a given bound infinitely many prime pairs with distance at most c, then the smallest distance with such property has to occur infinitely many times. So that means that this is equivalent with the existence of at least one Polignac number. So the bounded gap conjecture is equivalent with the existence of one Polignac number in both directions. So that means it's equivalent to it. Now, if we go back to the first result, it was Hardy-Littlewood who could just reach a non-trivial bound on the small gaps between consecutive primes, supposing the generalized Riemann hypothesis. It was Erdős who could reach the first unconditional non-trivial bound for the difference of consecutive primes. There were some 10 to 15 articles improving this result, and I just mentioned here the milestones, so to say. Bombieri-Davenport reached actually gaps of size at most half of the average gaps size, and combining their method with the method of Erdős, they could even improve this 1/2 to 0.466. And then later on, the most important milestone was reached by Helmut Mayer, 1988, which meant we have infinitely often gaps of size at most a quarter of the average size. And this remained the best result until 2005. So until 10 years ago, the best result about small gaps between primes was that we know that gaps of size at most 1/4 of the average size occur infinitely often. It's a little bit similar the case with primes in arithmetic progression, that our knowledge of 10 years ago was quite poor compared with the present knowledge. Now, we succeeded in 2000. These many numbers mean that when it was, let's say, in some sense made public through the internet, or some version arrived in a newspaper, in a journal, and when the final full article appeared in 2009, so therefore I use these several numbers. And this could be even improved to square root log n. And even just recently, we succeeded, based on a work with Balint Farkas and Szilárd Révész, we succeeded to find the optimal weight function, and with this to calculate the boundary of the limit of the original GPY method without any sort of improvement of a Bombieri-Vinogradov theorem, and this gave log n to 3/7 as a power. And fortunately, still this weight function, what we found, was useful in the Polignac project of Tao, and that could reduce the very large bound of Zhang. I mean, not just this idea, but this idea additionally helped to reduce the large bound of Zhang to a smaller one in the difference of consecutive primes. And a very important role is played by the uniform distribution of primes in arithmetic progression. So you see the formula. This is what we call for theta equal 1/2. It's the well-known Bombieri-Vinogradov theorem, but we put it in such a more general frame, and then EH theta, this notation was used in the blog of Terry Tao, and this means that the level of distribution of primes is x to the theta, and with other words, like an Elliott-Halberstam type conjecture is true for theta. I have to say that still in full generality, we don't know any theta bigger than 1/2 for which this result would be true, but nevertheless, such type of results helped in reaching bounded gaps between primes. So we call a theta admissible if this expression is true, and then the result theta equal 1/2 is a theorem, Bombieri-Vinogradov theorem. Theta equal 1 is a very deep conjecture of Elliott and Halberstam. And there are naturally any possible intermediate conjectures. Now, so that means the hypothesis EH theta means that the formula 1 is true for theta, and then we called theta as an admissible level for primes. And whenever you later will find the notation theta, this will always refer to an admissible exponent of the primes, but in some cases some restrictions will apply, and we don't need it in their full strength, but more in a restricted sense, which I will enlighten soon. And we succeeded in the same work to show that if EH theta, so that means if we can improve a little bit the Bombieri-Vinogradov theorem, then we get already bounded gaps between primes. In the optimal case, when theta is equal to 1, we will get C1 equal to 16. And now I quote Dixon's conjecture. This means that if we take n linear forms with integer coefficients, and there is no fixed prime divisor, so there is no local obstacle which could prevent to have all these coordinates to be primes, then we can get all these primes, all these numbers to be prime infinitely often. So for example, the pair n and n plus 1 is clearly not admissible, n plus 2, n plus 4 is clearly not admissible, but n plus 2, n plus 6 is already admissible. And this conjecture was a little bit later, and we call a k-tuple HK admissible if it does not cover all residue classes modulo P for any prime P. And Hardy-Littlewood made a conjecture in which they also quantitatively predicted the number of primes in a k-tuple, which is naturally a very, very deep assertion, so it's a far-reaching generalization of the twin prime conjecture for k equal 2. This would give an asymptotic for the twin primes below a given bound, and then even more difficult for general k. Now we will, I have to say there are two strategies. If you find a difficult problem, then you have two ways to avoid it. One way is to consider a weaker problem. This is the most logical. The other way is to consider a generalization of it. And as you see, we will use both strategies. And in some cases, really, it's even easier to prove a generalization of a theorem, for example, by induction principle, than the theorem itself. Here it will be not the case, but it will turn out that a generalization of a twin prime conjecture can be weakened to a form which does not imply the twin prime conjecture, but still implies a somewhat weaker conjecture, the bounded gap conjecture. So that means we play with both strategies parallel. And this, if I formulate this conjecture of Dixon actually in the special case where all AI are equal to n, that means if hk is admissible, then all of them can be primes infinitely often. And we introduce a weaker conjecture, DHL-K2. I mentioned DHL has nothing to do with the shipping company. It has to do with Dixon, Hardy, and Littlewood. And conjecture DHL-K2 means if hk is admissible, then n plus hk, so that translates, contains at least two primes infinitely often. So that means we get from this the bounded gap conjecture for if k is chosen arbitrarily. Naturally, if k is chosen to be large, then the whole assertion is more simple. So our goal would be to prove it for at least a large value of k. And because in this size, the gap size is at most the diameter of the set hk. And we proved that really if we have an exponent for the distribution of primes bigger than 1/2, then we have this DHL-K2 to be true for k if k is sufficiently large, which implies the bounded gap conjecture. Now, we proved one result with Motohashi. I listed here all the appearances in archive and in the 7 or 8 years ago in Bulletin London Math Society 6 years ago, and it's on my homepage as well. And what we assert that it is sufficient to prove this sort of improvement of Bombieri-Vinogradov type theorems for smooth moduli if the congruences are, we don't take the worst class, but if the congruence classes in the Bombieri-Vinogradov theorem are restricted to the solution of a polynomial equation in this respect. And that was what Zhang proved it in a different way, again without reference to our paper. He even did not answer any email in connection with this and did not add anything. Later on I heard that he used the method of some other people in later part of the paper without any reference, and then after 6 months somehow, and even did not reply any email of the relevant person, and then after 6 months reference still appeared in his manuscript. Now to go further, Zhang's theorem says that this improvement of Bombieri-Vinogradov type theorem is true for some exponent bigger than 1/2 in this restricted sense if moduli are smooth and congruence classes are as given. And from this he gets that this DHL conjecture is true for some large k, and he gets that primes have bounded gaps infinitely often, and then with a lot of efforts, the 7 million was improved to 4,680 by Tao's blog and Polymath project. And this is still independent from the Maynard's approach, about which I will just speak a little bit later. The Maynard's approach is somewhat similar, but it is based more on an elementary version of our work with Goldston and Yildirim, where also Sidney Graham was taking a significant part. And starting from this approach, he can prove that not only that we have two primes in bounded lengths, in intervals of bounded lengths, but even an arbitrary given number of primes, if the interval is enough large. I'm not quite sure, but I guess that m cubed can be dilated, but it's not so important. I had not enough time to check these several hundred pages in Tao's blog, but this doesn't play such an important role. Now, the work of Maynard and Tao says also that a positive proportion of all admissible k-tuple satisfies Dixon's k-tuple conjecture, so that means that all these are primes. I don't define what we mean by a positive proportion of all k-tuple, but you can guess it, what it means. And the next result of Maynard was that consecutive primes differ by at most 600 instead of the 4,700 of the Tao Polymath project, and then this was improved with several other ideas by Tao and the Polymath project to 270, and using the Elliott-Halberstam conjecture. Maybe I mentioned quite quickly and did not emphasize that our method would give 16 as the bound for the consecutive primes infinitely often, supposing the Elliott-Halberstam conjecture, and he could improve this bound to 12 under the same assertion. Now, another topic is the arithmetic progression in dense sets and in the set of primes. There were two famous conjectures, one of Erdős and Turan, that for every k we have infinitely many k-term arithmetic progression within the primes, and the Erdős-Turan conjecture that if A is a set with positive upper density, then we have many k-term APs within A for every k. And the solution, I give here just a short history of it. Semerady proved it for full generality, and as you see, it's quite a useful subject to gain good medals like Abel Prize, Wolf Prize, or Fields Medal. And even if we go further, then 10 years ago, still the best result was that we have infinitely many three-term arithmetic progression in primes, proved by Vinogradov's method. And then Green and Tao, the first versions, so to say, appeared in arXiv and so on in 2004, so just nearly exactly a little bit less than 10 years ago, and for this Tao win the Fields Medal. The methods combined all the known proofs for Semerady's theorem. And there is still another interesting conjecture of Erdős, that if we take a set whose reciprocal is infinity, then it contains infinitely many k-terms arithmetic progression for any k. This is not solved even for k equals 3. Also, Bourgain and later Sanders got very close to it, but it's still open for k equals 3 as well. Now, what I wanted to say here, that we can have a common generalization of these two theorems, namely that we can have constant d which is less than an absolute constant c, with the property that we have k-term arithmetic progressions of primes, such that for each element of the progression, the next prime is just p plus d. So that means both the original primes naturally form a k-term arithmetic progression, and naturally the p plus d, so their twin brothers, satisfy also an arithmetic progression. So if d would be 2, that would mean we have infinitely many twin primes, arbitrary long arithmetic progressions in the set of twin primes. So that means what we can prove is that we have arbitrary long arithmetic progressions in the set of generalized twin primes. The result is based on several earlier ideas, and the constant is if we use Tao's approach, then 4,600. If we use Maynard-Tao approach, then we don't need Motohashi-Pintz, and we don't need this Bombieri, Friedlander, Ivanez, Zhang, and we get just 270. So this is the best bound. Now, if we go further to Polignac number, so we said that 2k is a Polignac number if dn equals 2k infinitely often. Now, every positive even number is a Polignac number. This is Polignac's conjecture. And as I mentioned, the bounded gaps conjecture is equivalent that we have at least one Polignac number. Now, I can improve this to the fact that there are no infinitely many Polignac numbers, and even for their lower asymptotic density, which is supposed to be 1/2, we get something 5 times 10 to the minus 5. And this means that they form a set of positive density, so they are arbitrarily long arithmetic progression of Polignac numbers. And I proved still another result, that differences, so we have bounded differences between consecutive Polignac numbers, not only infinitely often, which would follow from the positive density, but always. Unfortunately, the C is ineffective here. Now, if we consider the normalized value distribution of dn, then the prime number theorem says us that the average value of dn normalized by log n is just 1. Now, Erdős raised the question that if we divide by this average distance, then his conjecture was that this dn over log n, so that this is everywhere dense in 0 infinity. For infinity, it was known already in 1931, but no concrete number was known for which this would be a limit point of the set dn over log n, despite the fact discovered by Ricci and Erdős 60 years ago that the set has a positive Lebesgue measure. And through the result with Goldston and Yildirim, we naturally got that 0 is a limit point of this sequence. And in some sense, I can improve it. But strangely enough, I still don't get any concrete number as a limit point, because I can prove that instead of just 0, we have a small interval, that all members of this interval are limit points of this sequence, but the interval is ineffective, the length. And we can work also with some sort of more fine distribution of the differences, so that means if I normalize it not with the log n, but take any other function which may take to infinity, go to infinity somewhat slowly, then we have still the same type of result, but again with an ineffective C. Now I have to mention that this ineffectivity has nothing to do with Siegel zeros. Now another interesting result is that Erdős could prove some 65 years ago that dn plus 1 over dn is a little bit less than 1 and a little bit larger than 1 infinitely often. And he asked the question whether this ratio could go to infinity, and he remarked that these conjectures seem very difficult to prove, which is up to some extent true, because for the proof we need some sort of generalization even of Zhang's result. And then what we can show that not only the limits are infinity, but the ratio can be as large as constant over log n, and we can also reach the formula number 9, which is, so to say, a mixture. I would say that using Maynard's result, we can. It's possible to get, so to say, longer increasing or decreasing sequences than just 2 consecutive elements. Now, another subject is that if we consider some old conjectures of Erdős about consecutive values of some multiplicative functions, then for the divisor function we have these were 3 important questions of Erdős and or Erdős and Mirsky, where omega n and little omega n defines the number of distinct prime divisors of n. And if we consider, for example, the result of Chen, then a version of the result of Chen can be written in such a way that 2p plus 1 is either a prime or a product of 2 primes. We believe that both possibilities occur infinitely often, and if the second possibility occurs infinitely often, then clearly 2p and 2p plus 1 satisfy these relations. So we have not only for the consecutive values the same value, consecutive arguments the same value of the divisor function, the omega function, but even simultaneously we can have for the same numbers d omega and capital omega to be. Now the problem is that due to the parity phenomenon of Zellberg, sieve methods alone cannot distinguish between integers having an odd and even number of prime factors, and that was the reason that these conjectures were considered as difficult as the twin prime conjecture, until Spiro observed that at least such a result can be proved infinitely often. Hisbram modified this idea to get dn equal dn plus 1, but it needed another 20 years until young Christoph Schlage-Puchta could prove the same for little omega n as well. And also concerning this parity phenomenon, a disadvantage of these results was that they could not specify the common value of these functions, even not the parity, the common parity of these functions. And now it turned out that we worked out a method which works for semi-primes, and we could prove with Sidney Graham that semi-primes are at distance at most 6 from apart, and then we could show that such results, so that means we could find arguments, infinitely many arguments, for which not only the little omega, capital omega, or dn takes the same value, but first they take the same value simultaneously. Secondly, up to some excluding some very small values, we can prescribe the value, the common value as well, which was not possible with earlier method. And so, for example, we get that omega n equals omega n plus 1 equals 3 infinitely often. And even the proof is very, very simple. It relies on a so-called basic theorem that if I consider some 3 linear forms without a fixed prime divisors, and I give a constant c, then for infinitely many values of n, we have at least 2 of these linear forms which have exactly 2 prime divisors, both larger than c. And from this one can give both we get the difference between consecutive semi-primes infinitely often. And we can prove also the result about consecutive values of omega function equal to 3. Namely, we can take 3 different linear forms which are clearly admissible, and then they have the property that a linear combination, as you see, of these forms are just give the some other form plus 1, and that means that if we suppose, for example, L1 and L2 have exactly 2 prime divisors bigger than a constant, then if I consider 3 times L2n and 4 times L1n, then they get 1 additional new prime divisor, so that means we get 2 consecutive numbers with 3 different prime divisors. So we can give a one-line proof using this basic theorem, which needs some 30 pages to show. So that's true. Now I would like to talk just quickly some ideas behind the proof of Zhang's theorem. So the proof relies, as I said, an improvement of the Bombieri-Vinogradov theorem, namely relies on, so that means this was the original theorem what we proved with Goldston and Yildirim, and then with Motohashi we showed that it is enough to consider it with for smooth moduli, and Zhang could show that this is true for smooth moduli if the residue classes are restricted as well. And so the ideas go back to Zellberg and Hisbrown, and since n plus hk in general contains only k over log n primes, so that means it seems to be we have not too much chance to get 2 primes in translates of n of hk. And so therefore the strategy is to use some weights which concentrate on numbers where n plus h contains many primes. Many has to be understood in this case as larger than 1. So that means once we get on average more than 1 primes in n plus hk, we get already sometimes 2 primes in n plus hk, and that means we get bounded gaps between primes infinitely often. Now the first approach would be to choose a function which is just 1 if all these numbers are primes and 0 otherwise. This is clearly good, but this is a tautology. Now we go a little bit further with this tautology, and if we consider this expression, then this is actually an analytic expression for the same tautology, apart that prime powers are allowed as well. So it doesn't seem to be useful. Now if we go a little bit further and we cut this, this expression at some value of r, this was Zellberg's idea, then the situation improves, but the problem is that the positivity disappears. Now this is still Zellberg's idea, naturally, to take square of this weight, and then we have positivity as well. And this was the first chanceful choice, and if I evaluate how many primes we get on average in such a k-tuple, then the answer is that this can be really evaluated as long as the parameter r is below n to 1/4. And if I evaluate it, we get on average 1/2 primes, which is not too much. So with this, we can't begin too much. Now the next idea was to be a little bit more modest, and we don't simulate or mimic the whole Dixon conjecture, but we would like to have at least, so to say, some primes in it, and we allow for some almost primes. So that means we consider the function a5, which means that the total number of prime divisors of this product phn is phn is the product of n plus hy. This has at most k plus l prime powers. And for this a5, surprisingly, we gain a factor 2, and we gain already nearly 1 prime per average. And unfortunately, the error terms are negative. So that means even if we take the best choice L equals square root k, we get a quantity a little bit smaller than k, a little smaller than 1. Now, fortunately, and with some additional ideas, one can still force out the small gaps conjecture. But what I will be talking today is that, on the other hand, if we consider and we suppose that this Bombieri-Vinogradov theorem can be improved a little bit, then instead of the 1 before, we have a factor 2 times theta, which shows that if theta is bigger than 1/2, then we are done, we get a quantity bigger than 1. And this means we get on average more than 1 prime in a k-tuple, and that means we have infinitely often 2 primes in a k-tuple. And with Motohashi, we showed that if we exclude the moduli which are not smooth or friable, then we lose just an exponentially small quantity. So that means basically the whole thing remains true. And what Zhang did was that he showed that it was possible to show with the above-mentioned restriction an improvement of the Bombieri-Vinogradov theorem, and using methods of Fouvry-Ivanets, Bombieri-Friedlander-Ivanets, Weil-Friedlander-Ivanets, etc., based on the theory of closed term sums. And he could prove, so that means he used quite strongly, just did not refer on it, the method of Fouvry and Ivanets. And this had a little bit strange form, so that means it did not refer for primes, but it referred for smooth numbers, so for the uniform distribution of smooth numbers. And the analogy is that the moduli are here rigid, so to say, but the numbers n are well factorable. And in case of prime gaps, we have a dual problem that we can factorize the moduli easily, and on the other hand, still the primes can be, so to say, roughly speaking, factorized using the method of His-Brown and Lignig's identity. And so in that way, it was possible to perform this method of Fouvry and Ivanets. And then another important issue was Friedlander and Ivanets' work, which referred for the distribution of D3n in arithmetic progressions. And so finally, what I want to mention is that one can generalize these ideas further in the sense that to show, which I showed earlier already, that the total sum of these weights are the same what we used earlier with Goldston and Yildirim, the total sum of these weights for those numbers where one of the coordinates has a small prime divisors. Small prime divisors means less than n to b, where b is a small constant depending on k. Then this is negligible if b is chosen enough small compared to k. And we also showed that basically one can take not only for fixed couples, but also one can choose h y to be as large as log n. And so finally, we could show the theorem 10, which says that there are infinitely many n's for which n plus he contains at least 2 primes. With the method of Maynard, it can contain any given number of primes. All the other components contains almost primes, and their number we can estimate from below with the true quantity. So that means apart from a constant, we can predict how much of these numbers we get, and we can weaken the assertion, we can weaken the condition to h less than log n. Now, some ideas behind the Maynard-Tao talk just very quickly. So you see that A5 was the weight we used, and A6 is a generalized weight with another weight function. And even with the optimal choice, we have a little loss compared to 1 unconditionally. And so that means we get a little bit less than 1 primes per average, which doesn't help. And unfortunately, Soundararayan could show that for any reasonably smooth function, we will have a little bit less than 2 theta primes on average. That means a little bit less than 1 prime per average. So that means it seemed to be that it's quite hard to go like this, and then we studied the problem and then worked out in a quite general class the optimal function f, and this improved a little bit on the dependence on k, but still we got naturally, according to Soundararayan theorem, a quantity less than 1. The idea of Maynard-Tao was that to use not only just one variable d, which divides the product of all n plus hy, but to take into account which n plus hy has which number as a divisor, and depending on the size of the divisor, to use a k-dimensional sieve approach. And then, quite strangely, he gets a quantity which tends even to infinity with k, and even the fact about log n doesn't play any role, so we can use, instead of Bombieri-Vinogradov theorem, the first result due to Rényi, and instead of just 2 primes, we got log k over 4 primes. That means bounded gaps between Pn and Pn plus 4 very often. And I just say that one can calculate all these things, and the final answer is a relatively easy function. So if you look for this f function, it is a relatively easy function, so once we work with k-dimensional functions, then we have this is not optimal for the variational problem, but still one gets a very good, nearly the optimal bound for this problem. So thank you very much for your attention. Yeah.
So thank you very much for your very interesting and dense talk. Maybe we have time for some few questions. Yes, please. We have to use a microphone.
What is behind your ineffective result if it is not Ziegel's theorem?
Yeah, it's a little bit similar. So that means if we have not just one large difference between Polignac numbers, but if we have something like 600 large differences between consecutive Polignac numbers, where every distance is, so to say, quite large compared to the first one, then finally we can give an effective bound depending on the first 600 large differences. So it's a little bit like Ziegel zeros, but it's not enough to have just one Ziegel zero, as if we would need 600 Ziegel zeros to get an effective bound for Ziegel zeros. So that means still the Bombieri-Vinogradov theorem is also ineffective originally, but that can be avoided in another way. So in some sense, the results where Bombieri-Vinogradov theorem are used are ineffective as well, but this can be fixed. But this other ineffectivity, I don't see any way to fix it. Yeah.
Any other question? Just a small question. You mentioned concerning the the more general Erdős conjecture. You say that Bourgain almost proved something in this direction. You are thinking about which results?
Which results? I will write it. Actually, so Bourgain got closer to it, but who got quite close to it, that was Sanders, and Tom Sanders. And he could show that if we have three-term arithmetic progression, let's see, I'm looking for some jokes, but, oh yeah, here. So if we have in a series three terms arithmetic progression, or I can formulate it in a different way. If A is such a sequence that its counting function AX is bigger than, so a little bit bigger than the primes, that means something, maybe, I'm not 100% sure, I guess log x to 5 plus little order 1, or 4 plus little order 1 over log x, which is a little bit more dense than the primes. Then there exist infinitely many three-term arithmetic progression in K. In A, where AX is naturally the number of elements of A which are less than X. And this is the result, a relatively recent results of Tom Sanders. So that means something 2010 and something. And Bourgain had earlier here x over log x2, I guess, maybe either 2/3 or 3/4, I don't know.
Thank you. Any other question? Okay, so let's thank the speaker again.